16th July 1945, Jornada del Muerto Desert, New Mexico. In the split-second bloom of the Trinity Test, a fireball expanded faster than anyone had ever photographed as the first ever nuclear test was carried out by Robert Oppenheimer and his team of physicists at Los Alamos.
Now I am become death, the destroyer of worlds.
The actual calculations of the energy released during this huge explosion was non-trivial due to the large number of physical and chemical processes involved in the detonation reaction. Yet, 5 years later, without classified data, Sir G.I. Taylor could estimate the bomb's energy just by measuring the radius of the blast on publicly released film frames. His secret? Dimensional analysis alongside Buckingham Pi Theorem, some complex math, and his mastery in fluid mechanics. But even without all of the latter, he was able to estimate the physical relation or the equation governing the blast with the mere toolkit of dimensional analysis. Today we learn the same toolkit, powerful enough for advanced physics, yet simple enough for a notebook margin, and by the end of this lesson, you should be able to recreate Taylor's Trinity estimate. First, what do we mean by dimensions in physics? A dimension is a fundamental attribute, be it length, mass, time, and so on, that we combine to describe any measurable quantity. They are the powers to which base physical quantities appear in a relation that defines another quantity. A dimensional formula, on the other hand, is simply the algebraic expression telling us which base quantities and with what exponents build a given quantity. For instance, length can be depicted dimensionally by L, time by T, and mass by the letter m. So for the sake of an example, if you think of speed, it equals distance divided by time. Translate that statement into dimensions and you get Lt to the power minus 1, which is a syntactic shorthand that must hold in any valid speed formula. Now, we have already familiarized ourselves with the 7 fundamental physical quantities while studying units, and you can check out my video on the same in case you missed out or you feel that you need to. The table here shows you the list of their symbols, their SI units, and dimensional formulae. Keep an eye on the rightmost column. That's the one we'll need throughout this video and use again and again. Whenever you encounter a new quantity, mentally translate it into one of these 7 building blocks. Now let's look at a couple of examples. First, let's take energy. It is equivalent to the work done, which equals force times displacement. Force carries dimensions mlt to the power minus 2, multiply by another L, and we obtain ml squared t to the power minus 2. Next, density. Mass over volume translates to m divided by L cubed, giving ml to the power minus 3. So this should also help you with identifying the correct units for physical quantities by spotting inconsistencies. Now let's test our newfound skills on working out an unknown dimension purely from physical reasoning. Consider Stokes' law for a small sphere falling steadily through a viscous fluid. The resisting or viscous force is given as F equals 6 pi eta RV, where eta is the coefficient of viscosity, R the sphere's radius, V the terminal velocity. For now, we can ignore the constants as they're dimensionless and simply focus on the variables at hand. We want the dimensional formula for the coefficient of viscosity eta. From the dimensional equation of force that we have written down, we can get that eta equals F by RV dimensionally, All that's left is to put in the dimensional formulae for force, radius and velocity into their appropriate places and simplify, which finally yields the dimension of eta as m L to the power minus 1 T to the power minus 1. So the SI unit for viscosity is kilogram meter inverse second inverse. And since 1 Pascal equals 1 kilogram per meter per second squared, this is thus equivalent to a Pascal second, which is something you can see on every data sheet of engine oil. Now let us try the same technique when the formula itself is already well known. Consider Lorentz force, which is F equals Q times V cross B, where F is the force acting on a moving charged particle in a magnetic field, Q the charge of the particle, V its velocity, and B the magnetic field itself. So suppose we are to find the dimensions of B. We first write the dimensional statement again, and from that we obtain that B equals F over Q times V dimensionally. So once again we substitute the dimensional formulae for each of them and simplify. Thus finally we arrive at B equals m times I to the power minus 1 times T to the power minus 2. Expressed in SI units, it reads kg ampere inverse second to the power minus 2, a combination given its own special name, the Tesla. Before going into the crux of our video, let's cement one indispensable rule, the principle of homogeneity and additivity. Every term in a physically meaningful equation must share identical dimensions. You can only add or subtract quantities that speak the same dimensional language. Think of it this way, 3 meters and 4 kilograms don't add the same way as oil and water don't mix. Actually, let's go ahead and test out this principle on the van der Waals law of real gases. As you may know from your chemistry lessons, the van der Waals equation modifies the ideal gas law to account for molecular volume and intermolecular forces, and the equation is shown on the screen. Not only does the principle of homogeneity allow us to check if the equation is dimensionally consistent, it also allows us to find out the dimensional formulae of the correction coefficients A and B. So let's see if we can demystify these empirical constants. First, look at the modified pressure bracket. Since P and n squared A by V squared add, their dimensions must match exactly. So we know that pressure is force upon unit area, allowing us to obtain its dimensional formula, and we also know that volume is simply length cubed and n is the number of moles. Thus we solve to obtain the dimension of A, which is simply pressure times volume squared over mole squared, and thus equals m times L to the power 5 T to the power minus 2 n to the power minus 2. Physically, A denotes the measure of the magnitude of attractive intermolecular forces within the gas. As for B, it's even simpler. Since V and n times B subtract, they share the same dimensions. Thus, the dimensional formula of B is simply L cubed n to the power minus 1. As for its physical significance, B represents the excluded volume per mole. Finally, time for the global consistency check. You can see that the entire left-hand side reduces to the exact same dimensions as nRT on the right. You can expand the brackets and check for yourself. Thus, homogeneity holds, the equation is dimensionally self-consistent. Now, what follows may already be clear to some of you from what we've covered so far. Nevertheless, let's go through the uses of dimensional analysis. First use case, it allows us to check whether an equation even makes sense. This follows directly from the principle of homogeneity we just saw. Once again, take the van der Waals equation of state. Every bracketed term on the left must carry pressure or volume dimensions so that the product matches the right hand side. Strip away the corrections and you recover the ideal gas law, PV equals nRT. Both versions reduce to PV equals mL squared t to the power minus 2, so both pass the dimensional test. But be wary about one thing. Homogeneity only allows us to check dimensional consistency of an equation, and it is silent about numerical factors. If I slip in one half, the dimensions still balance even though the physics is wrong. So dimensional analysis is a necessary condition but not a sufficient one when it comes to checking correctness of physical equations. But the insight drawn from it can still be useful in exams. Let's see how. Suppose you are given this problem. The orbit of a particle in a central force is given in a long and seemingly messy trigonometric form. 4 options list different constants a and b, and if you try the full mechanics, you'll burn through pages, but a 2-line dimension check isolates the answer. First, use homogeneity and calculate what a and b must be dimensionally. Since a multiplied by a dimensionless quantity gives 1 over r, the dimension of a must also be the same as 1 over r, that is L inverse. As for b, in order to be added with 1, b times c must also be dimensionless, and hence the dimensions of b must be the inverse of that of energy, giving m to the power minus 1 L to the power minus 2 times t squared. Only option A has dimensionally correct values of a and b, so we take it and move on, saving precious minutes. Moving on to the second use case, dimensional analysis allows us to guess functional forms even when the governing physical relation is not completely known and only a list of variables are given to us. Consider a simple pendulum of length L under gravity g. Suppose you are unfamiliar with the small angle derivation. What can the dimensions of these variables alone reveal about the time period t? You only know that the motion depends on 2 measurable quantities L and g, and that t must be a function of these two. Even in ignorance of the precise dynamics, dimensional analysis will fence in the answer. Let's start with writing the dimensional ansatz for t, as in a hypothesis that t equals c times L to the power x times g to the power y, where c is some unknown constant. Substitute dimensional formulae for t, which is time, L in length, and g, which is acceleration, and thus given as Lt to the power minus 2. Now if we simplify this and match powers on both sides of the equation, we get x plus y equals 0 and minus 2y equals 1, thus giving us y equals minus half and x equals half. Thus, if we put this in our initial ansatz for t, we get that t equals c times square root of L over g. Now say through some experiment, we find that for some L equals 1 meters and g equals pi squared meter per second squared, the time period is 2 seconds. If we plug in these values, we get c equals 2 pi, and voila! That gives us the textbook equation for the time period of the simple pendulum, which is 2 pi times square root L over g. Finally, the third friendly little rule, unit conversion. Say you need to convert 1 Newton of force into the CGS system. Let's set the stage carefully. We have the general equality given as n1 u1 equals n2 u2, which basically states that the numerical value times the unit must stay constant across the systems. Now insert the dimensions of force, which is ml times t to the power minus 2 in either system, so you get the ratios of each base unit, kilograms over grams, meters over centimeters, seconds over seconds, and powers are 1, 1 and minus 2. That multiplies out to 10 to the power 5 giving us 10 to the power 5 gram meter per second squared, or 10 to the power 5 dynes. Now it's time to take a leap into the subatomic extreme of scale, Planck's realm, with the smallest possible meaningful measures of physical quantities. Max Planck first developed the concept of these natural units based on the property of free space, drawing the definitions from universal constants alone, devoid of arbitrary human constructs. We will concern ourselves with only the 4 basic Planck units, which are based on the 4 physical constants found in nature, defining length, mass, time, and temperature. You can recall their SI units and dimensional symbols, which are shown here. Now for the universal constants. We have h bar, which is h over 2 pi, the quantum of action. Then there is Newton's gravitational constant g, c, the speed of light, and Boltzmann's constant kb. The table provides their units and dimensions as well, and it's clear that since the dimensions span only L, M, T, and theta, so any product of those powers of these 4 can yield every natural unit we seek. And you are shown how we can express any of these units in terms of these constants. For the sake of this video, let's focus only on finding out Planck's length. So we need to find out the exponents for each of the constants such that dimensional consistency is maintained. Let's replace each constant by its dimensional expression. You can gather each of them from the table. Now multiply and collect the exponents by individual terms. We thus arrive at this expression here. On the left hand side, Planck's length Lp has dimension of length, which is simply L, and this demands that the exponents of m, t, and theta on the right hand side vanish, while that of L yields 1. This gives us a linear system of 4 equations. 4 equations with 4 variables, and it's very easy, you can solve it on your own, and we'd get alpha equals beta equals half, while gamma equals minus 3 by 2, and omega equals 0. Thus Planck's length is the square root of h bar times g over c cubed. If you plug in the values of these constants, you'd get 1.6162 times 10 to the power minus 35 meters. That's roughly 10 million billion billionth of the diameter of a proton. Similarly, you can try to obtain the rest of the Planck's units. I leave those as an exercise to you. Now, all of this will allow us to finally do what we set out to do in the start of the video. Let's go back to the time of the world's first nuclear detonation. Now, what you see here on the screen are upscaled versions of single frames from the original high-speed film, each frozen less than a millisecond apart. Our task is to turn those flickers into something that can allow us to use simple dimensional physics to make an estimate of the radius and thus the energy of the explosion. Of course, as we do in physics, we first turn this into an idealized model, treating the blast as spherical in shape. This and the images we have allow us to plot the radius of the explosion as a function of time, which is given as milliseconds marked across each image. Due to the grainy film stock and parallax in optical tracker, we of course end up with some uncertainty, and the vertical error bars reflect that. So if we plot out the curve we get from the data, we see a quick empirical polynomial fit. It tells us that r depends on t, but we don't know the exact dependence of r on t. Meanwhile, the dashed line, which you are going to see now, is the prediction of Sedov-Taylor's self-similar blast theory, and in a while we'll gather by ourselves the result of this prediction by dimensional reasoning, showing r varies as t to the power 2/5. While we already know that r must be a function of t, since it's a dynamical process that varies with time, there are other variables it must depend on that we need to figure out. This is a more tricky task that requires some knowledge of fluid dynamics, but let's try our best here with intuition. So, energy E? Yes, it's relevant, as the more energy, the larger the blast. Think of fireworks in comparison with nuclear blasts. What about the density rho of the surrounding medium? Yep, that matters as well if you think about it, though it may not be evident at first. The heavier the medium, the more difficult it is to be moved aside by the shock wave. Here you can think of an explosion underwater versus one in air. Of course, the one in air will have more impact as air is a rarefied medium as compared to water, which has more density. Now, how about other variables like pressure or temperature? As the post-detonation shock is millions of times more intense than ambient conditions, the background pressure and temperature scarcely matter in the initial moments of the blast. As for mass, well, it is now accounted for by the energy which we have already taken into consideration, and gravity, it is negligible with respect to the shock's upward velocity. We are thus left with three active variables: time, energy, and density. At this point, we could attack the exponents exactly the way we did for the pendulum, plugging in the dimensions of E, rho, and t into the ansatz of R and match the powers. There is, however, a more general framework, useful once the variable list grows and the algebra gets messy, called the Buckingham Pi Theorem. In advanced fluid mechanics courses, it yields several independent dimensionless combinations called pi groups that capture a problem's entire behavior. But relax, for the problem we are dealing with, it involves only one pi group, and that collapses straight back to the simple dimensional matching trick you already know. But it's nice to see why the Buckingham Pi Theorem always works and how professionals extend it to tougher cases. Here's the promise of the Buckingham Pi Theorem in a single sentence. If a problem involves n variables and r fundamental units, then it can be reduced to n minus r dimensionless combinations, also called pi groups. In complicated flows, that might mean half a dozen groups, but for the Trinity blast, we are blessed with the simplest case imaginable. Let's count together and see. We have four variables among which we wish to find the relation between rho, r, e, and t, and three base units that make up these, which are m, l, and t. So n equals 4, r equals 3, giving us n minus r equals 1. So just one pi group can exist, and we are free to choose it as pi equals r times e to the power a times rho to the power b times t to the power c. One pi group means the blast radius must collapse onto a single power law, and thus we can write r equals k times e to the power a rho to the b t to the c, where k is a dimensionless constant, and hence obtain a, b, and c by dimensional balancing as we've previously done. We put down the dimensional expressions of each quantity and substitute those into the ansatz, and after a bit of math, we obtain a equals 1/5, b equals minus 1/5, and c equals 2/5. Plugging that back in gives us the final expression for r. If you overlay this on the Trinity data, you read k varies approximately in the range of 0.9 to 1.1, so k equals 1 is a reasonable assumption, one used by Sir Geoffrey Taylor in his paper. Putting in the value of air density and all, you would obtain the energy released close to around 21 kilotons of TNT, while the actual bomb at the Trinity site released about 25 kilotons of TNT with an uncertainty of plus minus 2 kilotons. So, The estimated value published by Taylor in 1950 was within 5% of the classified figure released later. He combined dimensional analysis with self-similar shock-wave solutions and other complex math well beyond our quick derivation to pin down the constant k, but the dimensional backbone we build today is identical to the first step of his analysis. So with that, we conclude not only today's video but this whole introductory sequence on units and dimensions. We began by asking a simple question. What does it mean to measure something? And 5 lessons later we have traced the evolution of units from metal bars in Paris to fundamental constants of nature, learned how significant figures and error bars guard every number we quote, mastered dimensional grammar well enough to unmask hidden blunders, scaled all the way down to Planck's length, and thereafter scaled all the way up to a nuclear fireball, recreating Sir G.I. Taylor's Trinity estimate within single-digit % accuracy. From here on, our journey takes on to the next stage. In the upcoming unit of videos, we will start building the mathematical toolkit that will make some of the stuff we have already covered easier as well as prove to be necessary for every topic that follows. So, until the next video, revise the playlists, solve some problems, and of course, subscribe to Eigen Akademie so you do not miss out on what comes next. So long.